on our look at different types of geographic data in mapping applications. So previously we discussed point data. Today we're going to discuss line data and also talk about the process of transforming data, geographic data, from one dimension into another dimension, and when and why you do that. Before we talk about line data, I want to go through a couple things with the previous lab. So you can see on this map of the earthquake data from Alaska, the cartographer does a good job segmenting out the different large earthquakes, having a nice um, data classification here, labeling the 5 largest. A couple things to note. One, whenever you have this really dark background and you have this red text, red is kind of a hard text to use anyway, just because it kind of gets a little muddled in terms of its contrast with background features. But you definitely want to make sure that you avoid having situations like this where you have your scale bar and your north arrow being so dark that you can't really see the difference, or you can't really see them very clearly. The next thing with this map specifically is this is using the firefly technique, as you can see here, but then it's enlarging the symbology, so creating a data classification within the symbology, but still using that firefly technique. And that can make it really difficult to actually see the quantitative differences between the different point values. So the firefly technique is good at showing a broad scale pattern. When you have a bunch of data and you want to see some sort of pattern that can be highlighted from that large array of data. Whereas when you do a data classification, where you're breaking up and creating different visual variables based on some sort of quantitative variable that's underneath the data, then you want to use a more simple symbology that's easier to see the difference between those data classes. So this one, for instance, does a good job of having a clean data symbology so you can see the differences between those small, medium, and large size earthquakes. This map, however, does not have a legend. So that's one thing you always want to have, is when you have these data classifications, is you always want to have a legend. This one also has some sort of issue with the scale bar. So whenever you're doing a project and the scale has this enormous number like this one, it's always good to kind of double check your projection and make sure that your scale bar is matched to your data frame in a way that is accurate. Otherwise, this map has some solid pieces. I'm not a huge fan of this kind of box over here, but that's just me. Another one that does a pretty good job with that data classification, here with the legend, though the legend could use more detail, and the labels themselves could probably be a little bit smaller, just so they're not taking up so much space within the map. But here's a good example of why it's important to go into the data classification attributes and shift the drawing order of your symbology, so that way the big circles are drawn on the top, medium, and small circles. And that way you get a little bit more clarity, like with this earthquake, right? We're more interested in seeing the large one than seeing kind of the array of small ones underneath it. Same over here. So changing that drawing order just allows you to see those prominent features a little bit more distinctively. And finally, another one that has a nice layout, a nice font design, nice legend, title, all the different elements that you want in your map look pretty good. But again, the symbology, having the firefly symbology, and also trying to use that with the data classification, makes it just so it's a little bit harder to read. So whenever you do the data classification of a quantitative variable, then you always want to make sure that's in a simple symbology, not the firefly symbology. And the reason I picked this map project is I have a friend that works at the Cascade Volcano Observatory and does a bunch of mapping of volcanoes and earthquakes and geologic features, and it's a good place to kind of look into if you're looking at doing this type of mapping. It's a good program that has many geospatial job applications within it. All right, so line data. So geographic line data is a type of vector data that represents linear features on the Earth's surface. So this can include roads, rivers, railways, pipelines, etc. Line data is known as arc data, and it has a defined starting point and a defined ending point within your geospatial database. So we often think of, road features like this as being line data. Hydrologic features, river systems, etc. One thing to note is that we don't really consider borders to be line data, but that's really the separation between two polygons, which we'll talk about polygons next week. And so the border itself is not necessarily a line, rather it's the edge of two polygons, unless that border has some sort of explicit linear feature like a fence or a barrier of some kind. So in that case, we would consider the border fence a line feature or a series of line segments, whereas the border itself is the edge between two polygons, right? And then we can see here the Rio Grande, that is a linear feature or line data of a river that also is the border between two polygon features. So, whenever we're thinking about that difference between line data and polygon data in regards to borders, it's good to, kind of give it a little bit of extra consideration just to ensure that you're not assuming something's a line data when it's actually the edges of two polygons. Road systems are often line data, and that ranges in types of complexity, right? We have an interstate system here, for example, that has very kind of simple line network, whereas if we scale into a city, we might have a much more complex line network with a different set of road hierarchies, whether that be expressways, arterial streets, residential streets, etc. And oftentimes when we have line data of public transportation system, for instance, we use what's known as a schematic model. And that way we simplify the line feature itself to make it more readable and to make it more generalizable. So in this case, this metro system here, these line features are not necessarily perfectly tied to the underlying geographic space, but rather it's a simplistic and generalized version of those line features to make it more readable to people that are navigating the system. So for instance, you wouldn't necessarily want to walk between this stop and this stop because that distance that is expressed in this map is not necessarily this distance that you'd experience on the ground, because the map is kind of shifted to make the map, or to make the stops a little bit more simplified. Another line feature that, or line data that is often worked with, is municipal infrastructure data. So a lot of people that go into GIS programs that work for the city, for city planning departments, or regional governance of various kinds, often look at line data that looks like this, with utilities, with street light networks, with pipelines, electrical lines, etc., etc. Often this is done using CAD software, and there is, a linkage between CAD and ArcGIS that you can use. You can take this data that's kind of computer drafted and then transform it into a spatial database. That process is a little gross. It's something you typically, if you go into municipal GIS, this is kind of the step that you learn on the job, because there's not really, each of these systems are pretty customized to the city specifically, and so like what you would learn kind of like foundationally maybe at one place, but then in another they'd have a different kind of data structure and different workflow format. And so each city would have its own type of like CAD GIS interface. It's kind of a clunky system, so you usually learn on the fly when you're hired at a place like that. But typically you'll see a lot of data that looks like this. Linear data that's tied to various types of municipal infrastructure. Another type of line data is path data. So this is, this is pipeline data as well. So infrastructure data and path data are two of the bigger, more complex ones. Here's like municipal infrastructure data that's often represented in CAD, regional or material specific infrastructure like natural gas pipelines or oil pipelines, would be data that looks like this. Again, it's all interconnected, it's all pretty messy, it's pretty difficult to work with in a lot of ways. River data often has a hierarchy to it, so there's different stream orders, and as you move down the watershed, that stream order becomes larger. So that's another component of linear data that can be challenging or you have to be mindful of working with, is the hierarchy that's embedded within stream and river networks. Here's an example of a map showing U.S. watersheds and kind of illustrating some of that different stream network hierarchy. And then the lab that you're doing this week is taking some path data, some animal GPS tracking data of elephant seals in the North Pacific, and just using some techniques to draw a little distinction or make these animal tracking paths just a little bit more visually pleasing, a little bit more captivating and engaging. So what we'll be doing with this lab is taking our GPS points of the elephant seals, transforming those points into line data, and then using what's called an illuminated background technique. So we'll take the line data itself and cast a shadow or cast an illumination from that onto our dark base map. And by doing so, then it provides like a canvas or a space in which we can then use the firefly symbology on top of that illuminated background, and it gives it a nice contrast where you can really see what pathways are most frequently used, what corridors exist with wildlife pathways or wildlife movement paths, and how that interacts with different features. In this lab we're using elephant seals because it's an ocean migration, and it's a little bit easier to kind of demonstrate the technique using the ocean backdrop as opposed to land backdrop, which is a little more complicated and whatnot. So just a simple lab to demonstrate how you can take GPS points from animal tracking collars, which are available at MoveBank and a lot of different databases have wildlife tracking data, both within ArcGIS Pro and also from both from within the Living Atlas and then from other platforms. So we're doing that, and then we're going to do a little Photoshop just so you can learn how to clip out something simple from an imagery, from an open access image, and put that in your map and kind of get rid of the background and whatnot. So probably a pretty simple Photoshop technique just to be able to add a little bit of character to your map. Here I have the elephant seal throwing up their movement paths. So a good little mini lab that kind of demonstrates a very simple technique to use with linear data. Okay, and then our second lab, so that's mini lab, or that's lab part 1. Part 2 is a bit more complicated. In this lab, we're going to do a data transformation of linear data into hex bin polygons. And so I'll talk a little bit about that process of data transformation, different dimensions of data to think about, and what that process looks like for this lab specifically, and also conceptually when we're talking about how to transform data from one format to another format. So that'll be part 2 of the lecture video. I'll go ahead and stop part 1 now, so it's not this kind of long rambly thing that you have to kind of sift through for the different parts of the lab. So this lecture just kind of introduced line data, went through some aspects of part 1 of our lab, and touched on some things with the previous lab.